Space Telescope is upsetting the apple cart all of a sudden. We realize that we may have to rewrite all the textbooks about the beginning of the universe. Webb just proved the universe existed before the Big Bang, shattering the widely popular idea that the universe came from nothing. The possibility that the Big Bang may be incorrect and that the universe might be larger and older than we think. Is there any truth to these revelations? And if so, then how did the universe come out to be? What cosmic forces are responsible for birthing entire galaxies? And what does world-renowned Michio Kaku think about it? Join us as we embark on a journey to uncover the truth, where we will delve deep into the Big Bang Theory and understand just how the recent data from the James Webb Telescope contradicts the latest standing theory, with insights from Michio Kaku. Understanding the Big Bang. In the endless expanse of the cosmos, one question has lingered in the minds of scientists throughout history. How did it all begin? For years, the Big Bang Theory has explained the diversity of life. According to this theory, everything that you see today, everything that existed years ago, and everything that will come to be in the future, all of it came from one very small ball with limitless heat and density. Scientists call this the singularity. The Big Bang Theory predicts that singularity underwent an incomprehensible expansion. From this expansion emerged the universe as we know it, with galaxies, stars, and planets taking shape over billions of years. Of course, there are a few other theories as well, such as the oscillating universe theory and the steady-state theory, to explain the origins of the universe. But none of them are as widely accepted as the Big Bang Theory. Keeping in line with this theory, everything in the universe came into being 13.77 billion years ago, which is how old the universe is, as calculated by NASA's Wilkinson Microwave Anisotropy Probe spacecraft. ESA's Planck spacecraft further refined it to 13.8 billion years old by recording the fluctuations in the cosmic microwave background. Astrologists collected data using high-power spacecraft and then applied Einstein's theory of general relativity to run the clock back to zero, the day it all started. Unfortunately, even with all the advancements in science and technology, scientists are still in the dark about the origins of the universe. The Big Bang Theory fails to answer some key questions about the series of events that gave birth to life and everything we know. However, what they do know is that it was very hot, and the explosion, or the Big Bang, which set things into motion, was greater than anything ever witnessed. The hydrogen bomb has a center that's around 100 million degrees Celsius and moves through the air at a speed of 300 meters per second. In comparison, astrophysicists believe that the Big Bang explosion registered a temperature of 1,000 trillion degrees Celsius and moved through the air at the speed of 300 million meters per second, making it 1,000,000 times hotter and faster than the hydrogen bomb. Although the information about these early days of life remains limited amidst this cosmic fog, scientists have managed to carve out a structure dividing these ancient times into distinct epochs. Starting with the Planck epoch, in this phase, matter as we know it had yet to emerge. Instead, the stage was set with time and a superforce, the progenitor of all the forces that govern our universe. Next emerged the Grand Unification Era, a fleeting span lasting a mere 10 to 36 seconds after the universe's birth. This epoch saw the strong nuclear force break apart. Following the Grand Unification Epoch, the inflationary epoch took the stage, marked by an explosive expansion. It was during this period that the universe underwent a dramatic growth spurt. Subsequently, the electroweak epoch took over, characterized by the electromagnetic and weak forces breaking free, as well as the universe's cooling and expanding processes. As the cosmic forces continued to work, the quark epoch came about. The universe still simmered with heat, preventing the formation of subatomic particles. However, the essential building blocks for the universe's future were present, laying the foundation for what was to come. Then came the last three chapters of the cosmic genesis: the Hadron Epoch, the Lepton Epoch, and the Nuclear Epoch. The universe, now equipped with the necessary ingredients, witnessed the birth of quarks, the elemental units from which protons and neutrons would emerge. These particles eventually joined forces, birthing atoms, the fundamental constituents of matter itself. Though the events during the Big Bang are more or less understood, what really intrigues scientists is the chain of events that set off these epochs. What existed before the Big Bang? Scientists believe that there was no space before the Big Bang. The explosion created space to expand through and essentially gave birth to the universe. Over the years, researchers all over the world have tried to recreate the events that led to the Big Bang for a more comprehensive understanding of the origin of life. What existed before the Big Bang? In fact, these researchers started way before particle accelerators and massive colliders. St. Augustine presented his theory about the origins of the universe for the first time 1600 years ago. According to him, God created time along with the rest of the universe. Unfortunately, St. Augustine's ideas were not widely accepted at the time until Einstein came along with his theory of relativity. According to the theoretical physicist, massive bodies in space bend time, essentially slowing it down. Keeping Einstein's theory in mind, before the universe's creation, the Big Bang held all the mass in the world, bringing time to a complete halt. So how can we discuss something before the Big Bang? Following Einstein's model, there is no before. Time did not exist before the Big Bang. That said, Einstein's proposition that nothing existed before the Big Bang directly contradicts one of physics' most basic laws, which states that one event makes another event happen, simply known as the cause and effect relationship. Say a ball is in motion. A force set that ball in motion. It simply cannot move it on its own. So how can something as significant as the birth of the cosmos come about on its own? Stephen Hawking has his own thoughts about what existed before the Big Bang. In his words, ordinary real time is replaced by imaginary time. He cited the Euclidean approach, which assumes that the history of the universe in imaginary time is a four-dimensional curved surface, much like our planet's curved surface. Hawking explained his point by asking everyone to assume imaginary and real time as beginning at the South Pole, a smooth point of space-time where the normal laws of physics hold. Since there is nothing south of the South Pole, there was nothing before the Big Bang. While the Big Bang theory does have a lot of holes, over the years, it's been solidified by many discoveries. In 1965, Arno Penzias and Robert Wilson discovered cosmic microwave background radiation uniformly distributed across the world. This radiation is, in fact, leftover radiation from the Big Bang, which can be detected from all around the universe, day and night. According to calculations, it first appeared 379,000 years after the celestial blast. However, evidence for the Big Bang theory existed way before Penzias and Wilson came along. Back in the early 20th century, Edwin Hubble used a special technique to measure distances to remote objects in the sky. What he found shocked the scientific community. Using spectroscopic redshift, Hubble found that these astronomical objects were moving apart, proving that the universe is always expanding. Yet, even as the weight of the evidence piled in favor of the Big Bang theory, scientists continued their search to uncover an alternative explanation for the universe's origin, since it could not answer one of the most fundamental questions about life. Inflationary quantum cosmology. Given the birth of leptons and quarks during the 6 epochs of the Big Bang theory, scientists considered applying the quantum theory to explain the origin of the universe. The idea first became popular among cosmologists in 1981 after years of struggling to solve the horizon problem. Let's say the universe is not expanding. Now imagine 2 photons simultaneously released into the cosmos, each embarking on an opposing journey, one destined for the North Pole, the other for the South Pole. Ideally, these photons can't have the same properties since they've had different journeys, but for some reason, these 2 photons emit cosmic microwave background information at exactly the temperature. So, somewhere along the way, these 2 photons must have interacted. But that's not possible since they were traveling in opposite directions. So, how did they interact? Inflationary quantum cosmology theorizes that at one point, the entire universe was in contact with one another and existed at the same temperature, sharing a fleeting connection. It expanded exponentially for some time after the Big Bang. Inflationary quantum cosmology also stands to provide a solution for the singularity problem. Cosmologists believe that following the principles of quantum physics, the universe itself came to be from a fluctuation. What's more, quantum physics relates the creation of the universe with the uncertainty of the vacuum. A vacuum refers to a state devoid of any particles, which is how the universe started, a big ball of nothing. But, keeping in mind the principles of uncertainty, the vacuum is never empty. Heisenberg's principle of uncertainty best explains the phenomenon. According to this theory, there exist certain properties which can't be measured accurately. Take, for example, position and momentum. If the position of a particle is accurately known, the less uncertain measurements about its momentum become. The same principle applies to time and energy. Scientists cannot accurately measure the energy and deduce the time of these events. So, Heisenberg's principle of uncertainty challenges the notion that all field values remain zero at the time of a vacuum. To put it simply, true emptiness simply does not exist. Whatever appears empty to scientists is actually changing at an unpredictable rate. The zero-energy hypothesis. But even with all its uncertainty and variability, a few things remain constant in the vast expanse of the universe. Take, for example, the zero-energy universe hypothesis. According to this theory, the total amount of energy at all times is zero, which means that the forces of positive energy offset forces of negative energy. In light of this notion, the massive expansive forces that gave birth to the universe must have been balanced by a negative force. What force emerged to counteract these colossal forces in the cosmic equation? It was gravity. According to this theory, the positive forces of stars and galaxies are balanced by the gravitational field. The idea was widely accepted by Stephen Hawking, who firmly believed in the zero-energy hypothesis. However, like most cosmic mysteries, matters are rarely as straightforward as they seem. Stars have a massive amount of negative energy. Interestingly, the smaller the star, the greater the pull of gravity. Once this negative gravitational pull exceeds the positive energy, a star collapses in on itself, forming a black hole. In the light of this idea, things cannot come from nothing. Even the void itself stands apart from true nothingness. Within this apparently vacant expanse, virtual particles blink into and out of existence. These minuscule particles, while fleeting, exert substantial effects on their surroundings. Bearing this in mind, Dutch physicist Hendrik Casimir predicted in 1948 that two mirrors placed in a vacuum would attract each other, owing to these very particles. Quantum physicist Pasi-Lahti-Maki at Aalto University in Finland and his colleagues took the concept further by proving that light can appear from nothing in a vacuum. How is that? According to Einstein's theory of relativity, the speed of light in a vacuum is constant, but depending on the property of the material it's traveling through, this speed of light can change. Using this idea, Lahti-Maki and his team of colleagues proved their hypothesis by exerting magnetic fields in a vacuum and changing the speed of imaginary photons, which led to the creation of real photons. So, what about the notion that the universe came from nothing? Taking note of the laws of quantum physics, the idea of something emerging from true nothingness clashes with the fundamental principles governing this realm. So where did the universe come from, if not the Big Bang? Quantum physics theorizes a random quantum fluctuation of the void heralded the dawn of creation. Before this fluctuation, the universe existed in the vast expanse as a ball of nothing for a time we cannot predict, since time did not exist before the Big Bang. This random quantum fluctuation kicked into motion a chain of events that gave birth to an entire universe. However, as we delve into this cosmic saga, a probing question arises. What catalyzed this profound quantum fluctuation that birthed life as we know it? Was it random? And if it really was random, what are the chances of it happening again? All scientists know is that in case a random quantum fluctuation does happen, prompting the universe to explode and expand one more time, it would wipe out life as we know it. The anthropic principle. Amidst these contemplations, scientists have stumbled upon an even more perplexing question. Could there have been only a solitary Big Bang, or perhaps a cascade of explosive events birthed multiple universes? While evidence to suggest the existence of parallel universes remains to be put forward, scientists have concluded even if such universes did exist, they would not be visible to us. Imagine a piece of paper, and our universe exists on this piece of paper. Now let's say another universe does exist. It would exist on another sheet of paper, but we'd be unable to observe it because said universe would be made by its own set of constants. While the universe remains unpredictable at large, there are certain factors that remain constant in this realm of uncertainty. Take, for example, the speed of light or the charge of a neutron. These are fixed constants in our universe, and the existence of life depends upon the values of these fundamental physical constants. So, if multiple universes did exist, say on a separate sheet of paper, cosmologists would not know about them, simply because the forces of nature that gave birth to life on that piece of paper cannot travel to ours. Cosmologists call this the fine-tuned universe. According to this concept, the smallest change in physical constants would give birth to a universe that's radically different from ours. But if something cannot be observed, does it really exist? In 1856, Robert Dickow proposed what's known as the anthropic principle. According to Robert, observations can only be made about a universe that can support intelligent life. Later, philosopher Nick Bostrom introduced the weak and strong forms of the anthropic principle. According to the weak anthropic principle, observers observe the universe in a state that suits life. On the flip side, the strong anthropic principle states the universe must have forces that support intelligent life. Meanwhile, a third principle, the participatory anthropic principle, states that no phenomenon exists unless it is observed. So, where does that leave parallel universes? MIT theoretical physicist Alan Guth, who came up with the theory of cosmic inflation, said that it's hard to build models of inflation that don't lead to a multiverse. Stanford's Andre Lind agrees with the sentiment, saying that new universes are popping up all the time, thanks to a unique process called chaotic inflation. Black holes. The theory of second universes is a work in progress. A small group of scientists, in fact, believe that our universe exists inside a black hole, and that every black hole gives rise to a universe. As impossible as it sounds, the theory is well supported and actually finds its basis in some of the most fundamental principles of physics, including the theory of general relativity and quantum mechanics. For years, physicists have been trying to merge these two theories. The theory of general relativity explains objects at the largest scales, while the theory of quantum mechanics explains objects at the smallest scales. Putting both of these in two separate realms, however, was a problem. In 1960, an adaptation of the general relativity theory called the Einstein-Cartan-Siama-Kibble theory of gravity combines these two separate realms of physics under quantum gravity. According to this theory, particles such as atoms and protons possess an internal angular momentum that grants these particles with torsion. This torsion would be a repulsive force resisting the attractive force of gravity. So, how does that tie into the creation of life? Think of a star collapsing. As we mentioned before, a star collapses under the immense force of gravity, overcoming the torsion forces. But with time, the torsion forces would gain strength and stop matter from compressing into a point of infinite density. This would bring the collapse to a stopping point. Matter would exist as an extremely large entity with finite density and concentrated energy. Following Einstein's principles, this energy would be converted into mass. With the addition of enough particles, the torsion forces would also increase, working directly against the forces of gravity. This unique dynamic of forces would eventually lead to a big bounce. Scientists theorize that it's this big bounce that's responsible for our ever-expanding universe. Michio Kaku has raised his own questions about the theory of cosmic inflation. He thinks that the theory of cosmic inflation opens up a can of worms. In fact, he compared the theory to a Trojan horse, saying that it opens the door to many bangs and many universes, which is understandable since it's the nature of quantum theory. More importantly, Kaku pointed out how the theory of cosmic inflation only predicts a bang and an expansion. It does not provide an insight into what the fuse was. Given the drawbacks, Michio finds himself leaning towards another principle of physics, the string theory. The string theory predicts an approximate number of universes around 10 to the 500th power, providing an explanation for the parallel universe. That said, almost all theories to explain the creation of the cosmos remain shrouded in doubt. The widely accepted Big Bang cannot explain certain aspects of the universe's creation. For one, keeping in mind the Big Bang, a superhot explosion should have generated a small amount of lithium and a large amount of helium. However, astronomers have found that the reality is quite different. The oldest stars in the universe were found to have an amount of lithium that is 1/10 of the predicted level, while the levels of helium are less than half the amount of the predicted values. What's interesting is that the theory has accurately predicted the current amount of other light elements generated by fusion reactions in stars. Moreover, the Big Bang predicted the production of matter and antimatter in equal amounts. Based on this assumption, the number of particle-antiparticle pairs should reduce the surviving matter density to approximately 10 to the 17 protons per centimeter cube. However, scientists found that the real observed value was far from the predicted value. It was recorded at 10 to the 7 ions per centimeter cube, which was more than 10 billion times higher than what the Big Bang predicted. Scientists believed they were wrong about the symmetry between matter and antimatter. In fact, some peculiar forces at work led to the production of more matter, thereby disturbing the matter density. More importantly, the Big Bang shrouds the theory that the universe is ever expanding in doubt. If the universe was expanding, objects at high redshift should appear larger and dimmer, taking into account the laws of optical illusion. Moreover, the ratio of apparent brightness to apparent area should sharply decline with redshift. Strangely, though, the surface brightness is completely constant with distance, which does not fall in line with the findings of an ever-expanding universe.